This video is going to go through section 8.6, which was how do you solve exponential functions or logarithm equations. So I tried to break it down into the different types that we went through in class. We basically went through 4 types in class. So I'm going to do one of each so that whatever you're faced with when you take a test or a quiz, you know what to expect and how to approach it. So the first type that I have up here is when you have an exponential expression equal to another exponential expression. And your goal here is to get them to be the same base. Kind of think of it as like equating bases. If they're both, get them both base 2 or base 4 or base 5, whatever base will work. In this particular problem, the easiest way to do it is to get both of them to be in base 4. And the reason that's easiest is because it allows us to keep the left side unchanged. So 64 is base 4 to the third, so 4 cubed. And now you want to use exponent rules, and what you can say is that 2x plus 1, the exponent on the left, is equal to 3 times x minus 3, the exponent on the right. You can distribute, so you get 3x minus 9, and then I'm going to subtract 2x from both sides. So I get 1 equals x minus 9, and then my last step is to add 9. So you get x to be 10. Don't really have to worry about extraneous solutions with the exponential functions. You can put anything in for an exponent, so that is not an issue. But if you do want to check your work, you can see in the very beginning, if you would have put a 10 in for x, would you get the two sides to be equal? Another way to do this problem is you could have put everything in base 2. That would be slightly more challenging because you'd have to change both the left and the right side. You would still get the same answer as long as you did it correctly, but this way that I did it takes a little bit less time, a little less work. The second type is when you have a single exponential expression in your equation. So you'll look right here, and the exponential piece that you have is the 5 to the x plus 1. First thing you want to do with these is you want to isolate that exponential piece. So I'm going to start by subtracting 1. So I get 2/3 times 5 to the x plus 1 equals 4. And then I'm going to multiply by the reciprocal to get rid of the 3/2. So I have 5 to the x plus 1 equals 4 times 3/2 is 6. Once you have it isolated, now you're down to the only thing that you have on the left is your exponential piece. You want to take the log of both sides with the same base as this base number. So I'm going to take log base 5 of both sides. Just kind of squeeze it in over here. When you do that, the log base 5 of 5 cancels, and you're left with just the exponent x plus 1. On the right, what you're left with is a piece, log base 5 of 6, that you can't figure out in your head, but you can use the change of base formula to figure out what it is. You can either take the common log of 6 divided by the common log of 5, or you can take the natural log of 6 divided by the natural log of 5. So I'm going to do the natural log of 6 divided by the natural log of 5. I'm going to go to my calculator to figure that out. Natural log of 6, close your parentheses, divided by the natural log of 5. So you're going to get a decimal, and you should expect decimals. So you get around 1.113. Subtract 1 from both sides, so my final answer is about 0.113. Again, with exponential pieces, you really should not expect any type of extraneous solution, but you can, if you want to check to see if your work is right, take your answer, put it back in for x, and make sure the two sides of the original equation are equal. The third and fourth type deal with logarithmic equations. So when you look at these, what they have kind of their common characteristics is you'll see a logarithm, whether it's a natural log or a common log or some other base log present. We're going to start with the first type, which is when you only have one natural log. When you only have one natural log, your goal is to isolate the natural log that you have. So I'm going to add 1 to both sides. So I have 4 natural log of x plus 3 equals 16, and then divide both sides by 4. So I have the natural log of x plus 3 equals 4. Once you've isolated the logarithm, you want to exponentiate is the word that I usually use. You want to take both sides to the base of whatever the natural log base is, or the log base is. In this case, we're working with the natural log, which is base e. So we're going to take both sides and have them be base e. Essentially, what was originally there has become the exponent, which is why I call it to exponentiate. The e and the natural log will cancel, so you're left with the x plus 3. And on this side, you have e to the 4th. Which, if you want a decimal approximation for that, you can go to your calculator, hit second and the ln button, and we take e to the 4th. If you want to just leave it as e to the 4th, you can do that. That's called an exact answer. It's actually a little easier, and you don't have to worry about rounding. We're going to take that answer, and then we're going to subtract 3 from both sides. So I can either write my answer as exactly e to the 4th minus 3, or if I want the decimal approximation, I can take what I just had, I can subtract 3 from it, and I'd say that it's approximately 51.598. Both answers are acceptable. The last type that we did in class is when you have multiple logs. And when you have multiple logs, you have to use your properties to condense it. Get it to a single log so that you can treat it like you just did in type 3. You want to get it to be one log. So if you have 2 or 3 logs, it needs to be condensed as much as possible. Most often it is what you're going to see up here where you have to multiply, use that product property. But you could also be using the quotient property. You could also use the power property. You're basically like putting it back together to a single log. So the first thing I'm going to do is I'm going to use my product property to multiply these together. So I'm going to have log base 4. When I multiply x times x plus 6, I have to distribute. I get x squared plus 6x. Once you've condensed it into a single log, you're going to do what you just did on the last problem, which is exponentiate. Take both sides to the base of whatever the log is. So the log is currently base 4, so I'm going to make both sides be base 4. The base 4 of log base 4 will cancel, so I'm left with x squared plus 6x. Be careful on the right. This is the most common mistake. That is not 4 times 2. That is 4 squared, so that is 16. You're left with a quadratic, so you need to get it in standard form. So I'm going to subtract 16 to get it equal to 0. I want to factor it. It does factor to x plus 8, x minus 2, which gives me answers of negative 8 and 2. With logarithmic answers, and this is something that you could also apply to the third one that we just did, you can have extraneous solutions. The biggest thing you're making sure is when you take the answer or answers that you get, if you plug them back into the original statement, you cannot be taking the log of something that is negative. That is not part of the logarithm's domain. So when you look at your two choices here, if you try to put negative 8 back into the original equation, whether you put it here or here, you're going to be trying to take the log of a negative number. That tells me that negative 8 is not a solution to my equation. 2 is fine. If I put 2 back in, I'd have log base 4 of 2 plus log base 4 of 8. Does that equal 2? You could check on your calculator. You could choose change of base if you want to check your answer. You could use properties to check your answer. In the end, that is our only solution. So when you come on your test to the section that asks you to solve, you want to think about which one of these types are you looking at. Are you looking at an exponential on both sides where you want to get them to be the base the same? Are you looking at a single exponential piece where you're trying to isolate it and take the log of both sides? Or are you looking at a logarithm piece where you're trying to isolate that, get it to be a single log and isolate that, and then exponentiate? Those are all of the types that you'll see when faced with a test over this chapter.